Hello and welcome back. This video covers Unit 6, Activity 4, numbers 1 through 5, Road to $1 million. You might recall in Activity 3 that we started with $2,600, and then after 30 years, the money was worth $9,062.70. Now let's look at this problem in reverse. Let's say that 30 years ahead, we are at retirement. So if we're at retirement 30 years from now, that means we are 0 years from retirement. And we would have $9,062.70 in the account. Well, let's say that we were 5 years out, 5 years away from retirement. We would need to put $7,359.95 in our account in order to have the $9,000 at retirement. Well, let's say that we were 10 years away from retirement. We would have to put in $5,977.16 in order to have $9,062 at retirement, and so on. So the further you get away from retirement, going 10 years away, 15 years away, 20 years away, the amount that you actually need to put in decreases because you have more time to save. And so as you see, when we drop down to the 30 years, that means you're 30 years away from retirement, you would need to put in only $2,600. All right, now question number 2, it says calculate the regression equation for the given data. Well, to calculate the regression equation, we need to decide if this is going to be linear or exponential. So let's look at the difference between each number. To get from the 9,000 to the 7,000, you'd be subtracting this 1,700. And then to get from the 7,000 to the 5,000, you'd be subtracting 1,300. To get from the 5,900 to the 48, you'd be subtracting 1,100. So what's happening is the amount that you're subtracting is getting smaller each time. So you could say that this is decreasing at a decreasing rate. Therefore, this is going to be exponential, and it's going to be exponential decay. So we're going to take our calculator, and we're going to type in all of this data into our calculator by pressing the Stat button. Now, you will need a TI-83 in order to do this. So here's the Stat button. We're going to press that, and you're going to select Edit. And then you're going to type in the numbers in the left column. That is the years of maturity, or years till maturity. That goes in the L1 column. And then the numbers in the right column, the principal required, goes in L2. And as you can see, I've already typed in the data in both columns. Once the data is typed in, you're going to press the Stat button again. And this time you're going to go to the top where it says Calc, using your right arrow. So go to the Calc menu. And then you're going to go down to where it says Exponential Regression. And select that. And then you'll press Enter. And then, and you might have to press Enter a couple of times, but then you will get this information. It'll tell you the equation, what the equation looks like. It's y equals a times b raised to the power of x, and it gives you the values of a and b. All right, so back to our page. We know the equation is in the form y equals a times b to the x. That's what an exponential equation looks like. And the a value is this 9062.68, and the b value is 0.9592, which we round. So our equation is 9062.68 times 0.9592 raised to the power of x. And then it says, explain why the function model you use makes sense in the problem. Well, we've already talked about how that the values are decreasing at a decreasing rate, which makes it exponential decay. And the fact that the common ratio R is 0.9592, which is less than 1, that tells us that this is exponential decay. So the explanation is The data is exponential decay because it is decreasing at a decreasing rate. Okay, here's question number 3. Josephine is 20 years old and wants to save $1 million for retirement in 50 years. Assume she invests in a savings account that earns at least the current rate of inflation. Determine how much Josephine must save today to reach her retirement goal. So now you recall the formula for the future value. Its future value is equal to the present value times 1 plus the interest rate as a decimal divided by n, where n is the number of times that your money is calculated per year, and then it's raised to the power of n times t. We know FV is future value, t is time in years, I is the interest rate as a decimal, n is the number of times that your money is compounded or calculated per year, and PV is the present value. So let's begin just writing this equation with the numbers that we have in this paragraph. The future value is $1 million. That's how much we want to end up with at retirement. It's equal to the present value. That's what we're trying to solve for. You know, how much do we have to put in the account today? And it's 1 plus, and then this interest rate is the current rate of inflation, which happens to be 7.5%. You convert that to a decimal, it's going to be 0.075. Now n is going to be 1 because we're doing this compounding annually, which is only one time a year. So that's the interest rate divided by 1, which is just going to be that same number, 0.075. And of course the exponent is n times t. Well, since n is 1, that's going to be 1 times t, and t is 50 years. So that's 1 times 50 is 50. Now we're going to solve this equation for the present value PV. Well, in order to do that, we would need to divide by this parentheses on both sides. So present value is 1 million divided by all of this in parentheses raised to the 50th power. Now we need to put this in our calculator. So let me bring up my calculator here. All right, and we're just calculating this fraction, 1 million divided by 1 plus 0.075 raised to the 50th. So let's go ahead and type that in. Typing 1 million divided by, and then parentheses. Make sure you start with a parentheses at the bottom there. 1 plus 0.075, close parentheses, and it's raised to the power of 50. All right, that's our value of 26,889.13. All right, now let's just carry that amount back over to our page, and there we have it, present value, 26,889.13. All right, here's number 4. Suppose that Josephine does not want to begin saving for her retirement immediately. Fill in the following table to show the amount of money that Josephine must invest to retire 50 years from now with $1 million based on the number of years that she waits to start saving. So in this first column, it is years of waiting to save. So if that is 0, that means she's ready to save now. Well, we already saw in the previous problem that if she's ready to save now, then she would put in $26,889.13. Now remember, the 0 means that she is waiting 0 years to invest, so she's starting today. That means she has a full 50 years for her money to grow. The 10 means that she's going to wait 10 years from now to start investing. So that means she would only have 40 more years left for her money to grow. So let's see what the principle is that's required. Let's get our calculator. And what we're going to do is we need to change that 50 years to 40 years. Because if she's waiting 10 years from now, then she has 10 less years to let her money grow. So the 50 becomes 40. So I'm going to just copy this and change the 50 to 40. All right, so I changed the exponent to 40 there. And this is our new amount. So that's 55,419.35. Let's go back to our page here. And there it is, the 55,419.35. Now suppose she waits 20 years from now to start investing. That means she would only have 30 years left to make the 50. So she would have 30 years left, so we would need to change the exponent over here in our calculator to 30. So let's do that. Change the 40 years to 30 years, and let's recalculate it. And we have this 114,221. And let's go back and put that on our page. So if she waits 20 years, then she would have to put in $114,221 in order to have $1 million at retirement. Well, what about 30 years? If she waits 30 years from now to start investing, then you know what we need to do. She would only have 20 years left to earn her money. So we just change the exponent to 20. All right, there we go. And so if she waits 30 years from now to start investing, in order to have $1 million at retirement, she would have to put in this much money. And that is the $235,413.15. Well, same thing with 40 years. If she waits 40 years to invest, then that means she would only have 10 years to go before retirement. So we change the exponent to a 10 over here. And then that means she would have to put in this much money. And that is over $400,000. So it's $485,193. $485,193.93. So that's almost $500,000 that she would have to put in order to have $1 million at retirement. Well, what if it was 50? That means 50 years from now, she's actually reached retirement. So how much would she need to put in the account in order to have $1 million at retirement? And 50 years is at retirement. She would have to put in the full $1 million. And then question 5. Suppose Josephine believes in spending now and saving later. How could you use the table from question 4 to convince her otherwise? Well, that seems obvious from the table that the longer you wait to save, the more money that you must start with in order to reach your goal. If she starts now, she would only have to put in $26,000 plus. But if she waits 50 years, she would have to come up with the full $1 million. All right, that concludes this video on questions 1 through 5. Stay tuned for a second video on questions 6 through 9.